Okay, here's number 5. So S&P's 500 stocks. Use the data from Yahoo Finance, the monthly rate of return. That's how means how much monthly you get since 1950. The average rate was 0.007233 and a standard deviation of 0.04. Okay, and it's normally distributed. So I'm going to draw that. Let's draw that first. So we have a middle at 0.007233. Okay, one deviation up is 0.04123, so let's see what that is. So 0.007233 plus one step up of 0.04135. So one step up is at 0.048, so that's this number right there. 0.048583. And if we go one step down, it's negative 0.034117. So one step down is negative 0.034117. Okay, so the center is right. So you could lose money pretty easily, it looks like. So that's what they're asking. What's the probability that the random selected month has a positive rate of return? Where is it above zero, basically? See, this is positive 0.007 and that's negative 0.03. So 0 must be right in here someplace. So they want to know what's the chance that it will be above 0. So they want that section. Okay, so it's just what's the area above 0? So we can just do normal CDF. So let's do a normal curve with a low of 0, a high of infinity, with an average of 0.007233 and a standard deviation of 0.04135. So it looks like there's a 57% chance, so 0.569, 56.9% chance your month is going to be making money. So 57% of the month's stocks made money. Okay. Treating the next 12 months as a simple random sample, what's the probability that the mean monthly rate of return will be positive? That is with n equals 12. Okay, so let's see here. I got to remember the formula. So the average of a sample is always the average of the entire thing. So the averages are always the same, but the standard deviation is different. So the standard deviation is, let's see, what is it? It's the original standard deviation divided by the square root of n. So it's the original standard deviation, which is it's the population standard deviation, which is 0.04135 divided by the square root of 12. So let's take a look at that one. So that's 0.04135 divided by the square root of 12. So our new standard deviation for the sample is 0.0119. Okay, so see, that's the original was basically a standard deviation of 4%. Now we have a standard deviation of 1%. Okay, so let's draw that. Okay, so the center, still the same thing. The average of the sample is the same as the average of the population. So 0.00723. But now one step up is only 0.0190. So it's that number. So 0.00723 go up 0.0119. So it looks like it's going to be 0.019. Okay, and then one standard deviation down from the center is negative 0.00467. Okay, so that's one up and one down. I'll spread it out a little bit. Okay, and they want the same thing. What's the chances the sample, the next 12 months are positive? So again, there's positive, that's negative, so zero's got to be right in there somewhere. So it's looking for positives of this sample. It's like, what's the chances of a year being positive? They want a grouping of 12. Okay, so let's just do the same thing. Second distribution, normal CDF with a low of 0, a high of infinity, the middle right there. The only thing that's different now is the standard deviation, which is 0.0119. So that looks like 7.728, 72.8%, which is what they've got over there. Okay, so it's just the difference between a sample and the overall population. If you know the population, you can figure out, you can take a group of 12 out of that and it looks similar, it just has a different spread. Okay, treating the next 24 months as a simple random, what's the probability the mean rate will be positive? Okay, so same thing, the average is still the average of the sample, so that's the symbol for sample, that's the symbol for population. They're still the same. The standard deviation, that's the symbol for standard deviation of a sample. It's the population, that's the symbol for population, divided by square root of n. So now it's just going to be 0.04135 divided by the square root of 24, since the sample size is bigger. So 0.04135 divided by the square root of 24 is 0.00844. Okay, so it's basically the same drawing. We still have the same middle, which is 0.00723. One down and one up is 0.00844. So 0.00723 plus 0.00844. So now one step up is 0.01567. And one step down is negative 0.00121. And again, they want to know that chances it's getting positive, so 0 would be right in between there again. They want to know all that. So second, normal CDF, low of 0, high of infinity. Standard the center is the same, but now the standard deviation is 0.00844. So we have an 80% chance that 24 months are going to be positive. Which is what she's got. Okay, do we really need to do it again? 36 months. So now the standard deviation is going to be the original divided by the square root of 36. So it's going to be 0.04135 over the square root of 36. So 0.04135 divided by the square root of 36. So now the spread is 0.00689. I don't think I'm going to draw the picture because it's the same kind of picture. We're going to have the center, we're going to have a negative one there, we're going to have a positive one there, and they want 0 and above. Okay, so it's second distribution, normal CDF. A low of 0, a high of infinity, the center there, but now the spread is 0.00689. So now it's 0.853. You have an 83% chance to have a 36-month spread that is possible. Oops, 853, that's what it says there, 853, which is what they have. Okay, so using this above, describe the likelihood of earning a positive rate of return on stocks as the investment time increases. In other words, what's happening to the likelihood of earning money as the number of months increase. So the more chunk of time you look at, the better chances you had of being positive. So see up here, it was we looked at the original, so that's basically 1 month. You had a 56% chance of making money over a 1 month period, 72% chance of making money over a 12-month period, 80% chance of making over a 24-month period, and 85% chance of making money over a 36-month period. So the longer amount of time you keep your money invested, the better chance you have of having a positive return. Okay, number 6. A survey of 2,306 Americans aged 18 and older conducted by Harris Interactive found that 417 of them have donated blood. Okay, obtain a point estimate for the population. Okay, so these are the ones, So these are the kind of problems that I did for you on that homework. It was like what we did together, only it was about proportions. So proportions mean percent. So here, it's like how many people. So it's labeled p hat. That means the proportion of your sample. So how many people did it? So 417 out of 2,306. That's what the point estimate is. So it's 417 out of 2,306. $417 out of 2,306. So that's just saying that that's the same thing as 18%. Okay, so that number, 400 out of 2,300, is 18%, which is what that is. It's like the average. And so here in a minute, we'll put that at the center, 0.181. We'll go up 1 step, down 1 step, up 2, down 2, up 3, down 3, and find proportions again. Okay, verify that the requirements for constructing a confidence interval about P are satisfied. Okay, I can't quite remember what these requirements are. Let's see. I think it's something like N P times 1 minus P, I think has to be greater than 10. So the number, which is 2,306, times the proportion, which was 181, times 1 minus 181. Let's see what that is. 2,306 times 0.181 times 1 minus 0.181 is 3341. And that is bigger than 10. I think that's what it is. You might need to look in your notes for what the conditions are or what the requirements are. Okay, so construct a 90% confidence interval. Okay, 90% confidence interval, so we have all of these people, so this is the entire population, this is everybody. Oops, so we have this population, which is everybody, and they took 2,306 out of that population. They took randomly 2,306. And then let's say they took another random 2,306 out of there. That would be different. And then they took another random 2,306 out of there. That would be different. So they take the average of this group, the average of this group. So this next picture is the average of all of the groups. Okay, it's still centered around the exact same average, but it's a little bit tighter. It won't be as spread out because when you're taking all of these, you don't get very many of these extreme values. So that's why it gets tightened up. So a 90% confidence interval. Okay, so the center is gonna, so we found out that the center is at 0.181. So the center is from our sample, so we just have one of these little samples, and from that sample, it looks like the center is 181, but we might have just by randomness got a few more positives than below. So maybe the real center, see, we thought the center was 181, but maybe the real center was more like 171, and we just accidentally got some high values. We flipped more heads than tails, things like that. And then another sample, let's say they got more tails than heads, and they were kind of down there. So we think, based off of our sample, we think it's 18%, but there might be a low end and a high end. It's going to be somewhere between there. That's what 90% confidence is. We want to say, okay, I'm pretty confident that the real answer for the real population, based off of my one sample, I think the real answer is somewhere, since my sample said 18, I think the real answer is somewhere between here. That's what we're trying to say. So we're looking for that plus and minus. We're going to say, okay, we're pretty sure it's 18% plus and minus some error. Okay, now I got to remember what the formula for that plus and minus the error is. Right off the bat, I can't remember it because we have our calculator will do it. So we're looking for a confidence interval made out of proportions. Okay, so there's confidence intervals made out of samples, like where you already know not made out of samples, where you know the average, and there's confidence intervals when it's a percentage. Okay, so this one is a percentage. So when we go to stat tests, we want a 1% confidence interval. So percentages use t-scores. Okay, so we want a z interval. So when it's this kind, we want a z confidence interval. Now the people that wrote the programs didn't put the word confidence in it, so it's just an interval, so a z interval. Okay, that might be the wrong one. Oh, there it is. They did put the word in front of it. I went down. I got to go down further. It's a 1% z interval. It's a 1 proportion z interval. It's A. The reason I knew I had it wrong was because it was asking for the wrong things. It's going to ask, okay, how many people said yes? So for this particular problem, 417 people said yes. And then, well, how many people were there? Well, there are 2,306 people. Well, what kind of confidence interval do you want? We want a 90% confidence interval. Okay, there it is. See, that's the low and that's the high. So our confidence interval goes down to 16765 and up to 0.19402. Now, what that plus and minus number, see, 18, this 181 is right in the middle of that. See, they gave it to us. There's the 0.181. That's the 417 divided by 2306. That's right in the middle. If we want to know what this margin of error was, we can just take the low end. We can take the 181.181 and subtract the low end, 1676, let's say. Let's say that's 168. See how that's 0.013? We could have done it from the top end also. If we take 0.181 and subtract 0.194, see, it's plus and minus the 0.013. 18.1 plus that is the top end, and 18.1 minus that is the low end. So here's our confidence interval. What we're saying is we're 90% confident the true proportion in the real, so we're 90% confident the actual proportion for the entire population is between 0.168 and 0.194. Okay, so when we take these samples, we're trying to guess what everybody would say. So we asked 2,306 people. We're trying to use that to guess what billions of people would say. Okay, a television sports commentator wants to estimate the proportion of Americans who follow professional football. What sample size would be obtained if he wants to be within 3 percentage points and 95% confident? Okay. So if he uses this as the center, okay, so the sample size. Sample size is okay. I'm going to grab this off. I had to go get my computer. I need to look this one up. Okay, so there's a formula for that. I'm going to send you this little thing because it's pretty good. I say it's pretty good. Okay, so for portions, here's how you find the sample size. It's p hat times 1 minus p hat, so that's the 53. That's the 53 right there, and then 1 minus 53 will be 47, times the z-score divided by the amount of error that you want, all squared. Okay, so let's put some numbers in all of that. So the sample size would be, this number right here is the 0.53. So they're asking, how many people do you have to ask if you want to be 95% confident and plus and minus 3? Okay, that's what they're asking. How many people do you have to actually ask if you want to be plus and minus 3 and 95% confident? So it's 0.53 times 1 minus 0.53. Okay, the error is this number, 3 percentage points, so that's 0.03. Now this z-score is the z-score for 95% confidence. So they want the spread to be this wide, so 95% confident. That means there's 2.5% in that tail and 2.5% in that tail. Okay, I did it like that because that's what inverse normal needs. It needs the tail. So if I do second distribution inverse normal, you put in the bottom tail, 0.025. So see, you don't even need to have that on your calculator. You can just say inverse normal the bottom tail. It's 196. So the z-score for 95% confidence is 1.96. Now it doesn't matter if it's positive or negative because we're going to square it anyway. Okay, so we'll just type all that in our calculator now. So it's 0.53 times 0.47 times 1.96 divided by 0.03, all squared like that. The number of people you need is 1,064. Which is where that came from. Okay, now, so this is A was given this 53 and 47. So they're using an old survey to try to estimate where they think the answer will be. But what if they don't have an old survey? Okay, if they don't have an old survey, you just always use 50-50. Okay, so if they don't have anything else, it's just 50 for the yes, 50 for the other side, and then the same thing. So the z-score was 1.96, the margin of error was 0.03 and squared. So if you know what it is, you do this side of 1 and then the other side of 1. If you don't know what it used to be, you just use 50-50. So if I bring those numbers back and type it all in again, and now put 50-50, Now the sample size is 1,068. So they're almost the same thing because originally it was almost 50-50 in the first place. See, that's almost 50-50. By changing it just 3 percentage points, it just needed 4 more people, which is the answer to this. Because originally, the original was almost 50-50 in the first place.